Yes,
Yeah.
sir.
Okay, I will start now. See here, in today's lecture is very important lecture. If you get this concept, you can apply this concept for all disciplines, and you will get the all steps of finite element method in this. Okay. Now here we are formulating the finite element equation for one-dimensional structural bar. Okay, and next I am going to describe the properties of the stiffness matrix. Stiffness matrix is the property matrix and it has some properties. Okay, it has some properties. Now, what are that properties that I will explain? And if you get these properties, you can get your results. Okay. Now, after that, we will solve some problems on 1D structural bars. Okay. Now, here these are the steps of the finite element method. Already we have discussed. The first is discretization, next is selection of proper interpolation polynomial, next is derivation of elemental stiffness matrix and load vectors, next is assembly of the elemental equations to obtain the overall equilibrium equation, next is apply boundary conditions, solution for the unknown nodal displacements, and then computation of the elemental stresses and strains or further calculation. Now, how these steps are used for solving the structural problems, that I will discuss, and same concept we can use for thermal problems. Okay. Now, here sequence is also important. We will go by sequence also. Okay. Now, first one is 1D structural analysis. 1D structural analysis. Now, how we can apply finite element method for one-dimensional structural analysis. Okay. Now, here this is the one-dimensional structural bar. One-dimensional structural bar. It is a way to forces, these forces, and here I have shown the direction in same direction, but direction of the forces in same direction, but it may be in opposite direction. It may be multiple forces. Okay, are you getting this? For uh, starting, I have taken this type of direction, but it should be in equilibrium. Then we can use finite element method. Okay. Now this is a structural member. Structural member. Okay. It has length L and suppose cross sectional area A. Okay. Now we want to do the analysis of this. That means we are going to formulate the finite element equation, and after that formulation of the finite element equation, what we are going to do? We are going to calculate the stresses and strains in this, and that completes the analysis. Okay. Now, first step in finite element method is discretization. Discretization. Here, detailed discretization we will discuss later, but here I will show you, I will tell you some basic rules of the discretization. Now, first basic rule is selection of the element for the discretization. Selection of the element related to the selection of the elements in the discretization. See here, if your geometry, you have to check the first geometry. If your geometry has uh, one dimension bigger as compared to other two dimensions, means here any or every geometry is made up of three dimensions, that means x dimension, y dimension, and z dimension. That is what we can say, uh, length, width, and breadth. That means in space, what we are calling it as a dimension in x direction, dimension in y direction, and dimension in z direction. If any one of the dimension is very big as compared to the other two dimensions, like for example your push rod in the engine, it has length very high as compared to the its diameter. Okay, that means length is bigger, or one dimension is bigger as compared to other two dimensions. In this situation, you have to go for one dimensional element. Now second type of geometry is two dimensional geometry or two dimensional element. If dimension of the problem, or dimension of the geometry, or dimensions of the geometry in two directions are big as compared to third dimension. Okay, as compared to third dimension, that means if you consider the monitor of the laptop or monitor of the desktop, it has two dimensions bigger as compared to third dimension. That means thickness. third dimension. In this situation, you have to go for two-dimensional elements. Again, one more thing, if you observe the papers have two big dimensions, and third dimension is very small. Then in this situation, you have to go for two-dimensional elements. Two-dimensional elements are rectangles, then triangles. These are the two-dimensional elements. And if all three dimensions are bigger, then you have to go for three-dimensional elements. That means if we consider the CPU, or if you consider the piston, then piston, all three dimensions of the piston are bigger. That means are comparable, we can say, are comparable. In this situation, you have to go for three-dimensional elements. Have you got it? Have you got it? When we have to go for one-dimensional element, when we have to go for two-dimensional, and when we have to go for three-dimensional. Here, uh, if one dimension is big as compared to other two dimensions, then you have to go for one-dimensional element. If one dimension is big, then we have to go for one-dimensional. If two dimensions are bigger, then we have to go for two-dimensional, and all three dimensions are comparable, then you have to go for three-dimensional. Okay, three-dimensional elements. Now, three-dimensional elements are tetrahedron, hexahedron, like that. Can you get Mahesh Jalte? Mahesh Jalte. Mahesh. Mahesh. Pandit Srinivas. Pandit,
Yes, sir.
can you tell me when we have to go for one dimensional, when we have to go for two dimensional, when we have to go for three dimensional? You see here, I will tell you here, you have three dimensions for each problem. You
Yes,
have
sir.
x,
Hello.
y, z. Am
Hello.
I right? Ah, yes. Yes. Any doubt? If
Hello.
yes, yes. If you have any doubt, you can ask me.
Yes, sir.
Ah, can I go for next?
Yes, sir.
Okay. Now here you have seen the basic rule for the discretization. After this basic rule, we will start the discretization of this problem. Now see here. Now what I will do, I will assume this problem has small cross section as compared to its length. That means cross sectional area is small as compared to length. Okay, that is one dimension in longitudinal direction is very big as compared to the lateral two dimensions. That means here it has cross section like this. It has cross section like this, but this cross section is very small as compared to the length. So I am going to select the 1D element, one dimensional element for this problem. Now after selecting the one dimensional element, next question is how many elements we have to select. Next question is how many elements we have to select. Now you have to remember this basic rule. This is helpful for solving the numericals on this structural bar. See here, if there is sudden change in the geometry, okay, and sudden change in the loading, sudden change in the material properties, then you have to go for more number of elements. Okay, means if geometry is suddenly changing at certain location, at that location you have to put the node. Okay, if loading is suddenly changing, then also you have to put the node at this location. Okay, and if your material is changing suddenly, then also you have to use more number of elements. That means if you have this type of problem, you see here this type of problem. Okay, if, and it is a one dimensional problem, so, suppose, and here at this location your geometry is suddenly changing, therefore you have to use more number of elements for this type of problem. Up to this you have to use one element, from here to here you have to use other element. This is about the geometry. Next, if if same geometry, if problem is having same geometry, but loading is changing suddenly At this location there is some load. At this location, if you have extra load here, and at this location you have third load. See here geometry is constant, uniform, but loading is changing suddenly at this location. So you use element up to here for first part and second element up to here for second part. Okay. Now third case, if your material is different, suppose geometry is same, uniform, loading is at the ends only, but your material from here to here, that means from first end to this midpoint or at any intermediate section, this material is different, that is your M1, and this material is different, suppose it is M2. Okay, any number of materials are there. Then you have to select one element from here to here and one element from here to here. Okay, or now see here, by considering these things, you have to select the elements. Now what I will do for initial level, I am assuming this as a uniform geometry, constant geometry, that is a one-dimensional geometry, and loadings are applied at the ends only, and material is uniform, that is material is constant from first end to the last end. So we can use only one element for this type of problem. Okay, now I will discretize this by one element. You see this one element, this is the element for your problem. This is a discretization. I have discretized this by one element. Now while using this one element, here we are developing this in coordinate system. We are meshing that geometry in coordinate system. Here this one dimensional element, it has two nodes, and node number 1 is at the location xi and node number 2 is at the location xj, and distance between xi and xj, this distance, it is your length of the domain, that means xj minus xi is the length of the problem. Okay, we have discretized this by one element, only one element. It has node j at this location, node I at this location. Okay, and this node is located in a space at xi location, that is xi is the coordinate of node number I, xj is the coordinate of node number j. Okay, xj is the coordinate of node number j. Now this is a discretization. Now for initial case or for simplicity, we are assuming this displacement of node I is ui. That means when we apply the force on this domain, that means when we apply the force on this problem or this structural member, we will get the displacement of node I. That means this node will displace from its location, and this node is also going to displace from its location. Suppose displacement of node I is ui and displacement of node j is uj. Our aim is to find these displacements. Suppose this is ui displacement and this is uj displacement. See here, this ui displacement and uj displacement, it is the result of the problem. That means this is after solving the problem. Here don't go for this ui and uj, just you have to remember it is one dimensional, one element with nodes, with two nodes, and position of that nodes is xi and xj. Okay, now this completes the discretization process. See here, this is only one element, therefore it is simple one. If more number of elements are there, then you have to use more rigorous analysis is required. Okay, now this completes the discretization of this problem. Now after discretization, what is the next step? If you are doubt in discretization, you can ask me.
सर ते I आणि J का म्हणजे असं नोटेशन दिले?
You can do any notation. I and J, we are using subscript I and J as a standard notation. Na? It is just a subscript.
Okay.
You can use 1, 2 also.
हॅलो
Yes.
हॅलो सर
Yes.
सर ते आपण नोट्स दिल्यात एक्सरसाइज जे आता एकदा सर नोट्स दिल्यानंतर ते फोर्सचे एरो सर दाखवायला पाहिजेत.
हे फोर्सचे arrow काय? See here, this is force is the application of boundary condition. Okay, that will come in that step. It will not come in the
सर पण
discretization.
आता जर कंटिन्यू सर जर मोठा प्रॉब्लेम असेल तर कसं म्हणजे कारण की पुढला नोड सुद्धा येणार ना आता समजा
yes.
सर अजून एक
Yes,
लेंथ
yes.
पुढे असते
I will show you. If you have this type of problem,
अरे सर सांगतील ना
huh? If you have this type of problem, suppose it has forces at this location. Suppose say here in actual problem there may be support or there is a support. Maybe means there is this compulsory support. Okay, if you have force at this location, if you have force at this location. Okay, are you getting this? Now it's a discretization is like this. Here up to this it has one element. Okay, up from here to here it has one element. Okay, now before application of the force you write the stiffness matrix for these elements, you write the global stiffness matrix, you write the finite element equation, then you have to apply the forces as per the forces applied in the problem. Okay, मग जसे प्रॉब्लेम मध्ये फोर्सेस अप्लाय केलेत ना तशा तुम्ही बाउंड्री कंडिशन अप्लाय करायचे आहेत आफ्टर डेरिव्हेशन ऑफ द फायनाइट एलिमेंट इक्वेशन. दॅट आय विल शो यू. ओके, एनी डाउट? Any other? If you have doubt, yes. Okay, I will go to the next. After discretization, your next step is selection of interpolation polynomial. Selection of interpolation polynomial. So here in selection of interpolation polynomial also we have second unit totally on the selection of interpolation polynomial. Here I will show you simple interpolation polynomial. I will derive the simple interpolation polynomial. And see here, if your element is two noded element, then you have to use the linear interpolation polynomial. You have to use linear equation, just linear equation, and that linear equation is for the variation of u. Here your field variable is u, displacement, variation of the u over domain. That means you write the interpolation polynomial. Interpolation polynomial means it is a linear equation. Linear equation in terms of the coordinates for the variation of the displacement. Okay, now you see here I will write this interpolation polynomial. See here, this is linear equation. Is it visible? This is a linear equation for u. U is equal to a plus bx. Okay, you have two noded element, that means elements having two nodes, therefore interpolation polynomial is linear. Okay, linear. So here while writing the interpolation polynomial you have to follow one rule, that means you should have at least one constant term in the polynomial. Okay, and one variable term. Agree with this? That means your u is varying linearly with x. If you see the your problem in coordinate system, see here, this is your problem in coordinate system. This is your x coordinate axis, and this one is your y. Y is your u. Okay, u is varying linearly with x. U is varying linearly with x. That is your interpolation polynomial. It is very simple. That means here u follows the path of this equation. That means u follows this equation while varying in this element or in this domain. That means it is varying like this linearly. Here at this location you have value of u is equal to ui, and at this location value of u is your uj, that we are going to calculate. Okay, now next one, if this is the interpolation polynomial, then see here, this equation should be satisfied at this I node and j node. Okay, if this is the variation of displacement, this displacement equation should be satisfied at I node and j node. Okay, I node and j node. Now one more thing I want to tell you here. Here this a and b, these are the two unknown constants. These are the two unknown constants. So here, if these two constants are unknown, then we cannot find the value of displacement at any point between I and j. Okay, between I and j. That means if A is unknown, B is unknown, we cannot get the value of u at any point between these 2 points or between these 2 nodes. Okay, so we have to find the value of A and B. Now how this value is calculated? This value is calculated by displacement of node I and displacement of node j. That means from the ui and uj. Now if this is the equation for displacement, I can write equation for ui, I can write displacement for uj. Okay, now can you tell me what is the equation for ui? Can you tell me what is equation for ui? Yes, you see here ui, this is the element, this is the ui, am I right? Ui is equal to a plus bxi, because at node I your displacement is ui and at node I coordinate is xi. Therefore from this equation, if I put x is equal to xi, I will get the displacement at node I. If I put x is equal to xj, I will get the displacement at j. So you will get these two equations, that is ui at node number I, uj at node number j. Okay, now these two equations we can solve and we can find the a and b. Now see here, solve these two equations and find the a and b. Now when we solve these equations, I will get a is equal to ui xj minus uj xi. You can see here, first I will solve for b. Okay, you see here, if I subtract third equation from the second equation, what I will get? I will get b into xi minus xj is equal to ui minus uj. I will change the sign on both sides because xj I am assuming bigger. So I will get the b into xj minus xi is equal to uj minus ui. Do you agree with this? b into xj minus xi is equal to uj minus ui. I will write here for b uj minus ui equal to b into xj minus xi. Okay, do you agree with this? Now this xj minus xi, what is this? This is the length of element. Okay, length of element. Now you will get b is equal to uj minus ui divided by xj minus xi, that is uj minus ui divided by xj minus xi, but xj minus xi is length of the element. Now next one, when we put this b in this equation, any one of these equations, suppose I am going to put in this equation, in first equation, when I put b in first equation, what you will get? You will get a is equal to ui xj minus uj xi. See here, this is simple one, you can solve yourself also. Ui xj minus uj xi divided by xj minus xi, when we put this b in this equation. Okay, now after getting this a and b, see here, now a is function of ui xj uj xi l. Okay, b is function of uj minus ui divided by l, that is a and b, these are the functions of nodal coordinates. These are the functions of xi, xj and ui, uj. Okay, now you put these values in the interpolation polynomial. That means you put this a and b in this equation, that is in equation number 1. Okay, now you see this one here, a and b I will put in the equation 1, that is u equation. Now u is equal to, I will show you how it will be coming. I will show you. Now u is equal to, I will write here, u is equal to a is this one, a in a is as it is plus bxi, can I will just okay, I will show you how to solve this. Here it is. Here it is. Is it visible now? If you are doubt in visualization, you can see it. Okay. Now I will type one equation. I will write one equation here. You see here, u is equal to a. A is ui xj minus uj xi and whole divided by L, okay, plus b is I will use bracket uj minus ui divided by L into x. You will get this equation. Am I right? You will get this equation. You can see here. Okay. Now this is A, this is B, and when we put this in equation number 1, you will get this equation. Okay, means this is the your interposition polynomial now. Now if you observe this interposition polynomial, u is function of ui and uj and xi and xj. Okay, that means here if you know the values of ui and uj, you can calculate the value of u at any intermediate point on the element. Okay, now see here what I will do, I will combine the terms of ui. Now what you will get here, ui is this, here it is one ui, here it is one ui. Okay, now what you will get here, xj minus x divided by L into ui. Okay, xj minus x divided by L into ui. Okay, second term x minus xi, that is uj term. You see this uj term, this is, and one, this one, that is uj into x is there. Okay, x minus xi divided by L into uj. Okay, now this you will get, you see this one, you compare this equation and this equation. Is it same equation? These two equations, whether these two equations are same or different, you check
Same,
it.
sir.
If you have doubt, you can ask me, you can stop me and you can ask me if you have doubt in any step. Okay, you will get this.
Hello.
Yes.
yes
सर
ते जे x आहे
हा.
म्हणजे uj मायनस ui
हा.
अपॉन एल इंटू एक्स आहे, मग ते एक्स आतमध्ये मल्टिप्लाय करून मग त्याचं ते केलं नाही चालणार त्या तसं?
हा, चालते की, this you have to multiply with this one, na, these two terms.
हा
Am I right?
हा.
This term is uj into x. Am I right? And second term is ui into x. That's why you will get this term, that is, you see here, ui into xj, and here you will get ui into x. Okay, now when I take ui common, I will get xj minus x into ui. You see this one. Okay, have you got it?
Yes sir, yes.
And this is second term. Okay, see, it is simple mathematics, very simple mathematics. Okay, now you will get this equation. Now if you observe this equation, see here xj is a coordinate of node j, and x is a variable term, that is any location on the element. Okay, ui is the displacement of node number I. Next, x is the variable again, xi is the coordinate of node I, and uj is the displacement of node j. Okay, now when you get ui and uj, you can calculate the displacement at any point on the element. Am I right? Displacement on any location x. This is known as the interpolation of the result. ह्यालाच आपण इंटरपोलेशन म्हणतो. म्हणजे तुम्हाला हे नोडचे डिस्प्लेसमेंट मिळाले ना, त्या यूज करून तुम्ही कुठल्याही पॉइंटला डिस्प्लेसमेंट काढू शकता. इट इज अ स्पेशालिटी ऑफ द फायनाइट एलिमेंट मेथड. ओके, you can find the displacement at any location on the element. Okay, so we can get the displacement of each and every point on the domain. Okay, are you getting this? Or any required point on the domain irrespective of the meshing. Okay, now what I will do, next what I will do, I will replace this by Ni and this by Nj. That means here Ni is xj minus x divided by L and Nj is x minus xi divided by L. What I will do, I will show you here. You see here, this is your equation number 6. Now this I will replace by Ni and this I will replace by Nj. Okay, now your equation becomes U is equal to Ni and Ui plus Nj Uj. Okay, now Ni equal to your xj minus x divided by L and Nj equal to the x minus xi divided by L, and this Ni and Nj are known as the shape functions. You have to remember this. Okay, xj minus x divided by L. Just I have taken one single notation for this term, and one single notation for this term. This is your Ni and this is your Nj. Okay, and by replacing this by Ni and this by Nj, I am going to write U is equal to Ni Ui plus Nj Uj. Okay, and Ni equal to this one, Nj equal to this one. See here, Ni and Nj are the shape functions, and number of shape functions for the elements are equal to the number of nodes, and shape functions are functions of the coordinates. You can see here, it is xj minus x upon L, means it is again xj minus xi. Here x minus xi divided by L. Here Ni is function of coordinate, Nj is also function of coordinate. Okay, now one more thing I want to tell you here, that is, if I calculate the values of the shape functions Ni, Ni at node number 1, that is node number I and node number j. Here I will paste here this one. Now can you tell me what is the value of shape function Ni at node I? Can you tell what is the value of shape function Ni at node I? Can anyone? Ni at node I? Yes? Mahesh? Can anyone tell the value of shape function Ni at node I?
xj minus xi upon L.
Xj minus xi upon L. What is xj minus xi?
L.
L. And L by L is
1.
1. That means shape function Ni at node I is 1. Okay. Now can you tell me what is value of shape function Ni at node j? Yes, at node j. Ni at node j. 0. Okay. Ni at node j. Ni, I will write here, Ni at I it is 1. Okay, and Ni at j it is 0. Okay, same thing you repeat for this Nj. Now Nj at I. Now what is value of Nj at I?
0.
0. And Nj at j?
1.
Nj at j it is 1. Now what we can conclude from this? You see here shape functions at its own node, that means Ni at I is equal to 1 and at other nodes it is 0. Okay, Nj is 1 at node j, but it is at 0 at node I. Okay, where is this? That means shape functions at its own node are 1 and at other nodes it is 0. This is one important property of the shape function. Now when I take the addition of these two shape functions, what you will get when I take the addition of these two shape functions? Ni plus Nj. Ni plus Nj. What I get? What I will get?
1,
Ni
sir.
plus
1.
1. That means here it is at any location x. Am I right? Here, when we take the addition of shape functions at any point on the element, it is equal to the 1. These are the some properties you have to remember. That is, shape functions are functions of the coordinates. Shape functions have value equal to 1 at its own node, and it has value equal to 0 at other nodes. Okay. Now, next one. Next, this is known as the interpolation polynomial. Okay. This is known as interpolation polynomial. This one. Equation number 7. Here, by this we can get the value of u at any point on the element. Over. Now, after calculation of the interpolation polynomial, what is next step? What is next step? What is next step? After interpolation polynomial? Next
Hello,
is
sir.
yes.
सर
हा.
ते चौथं इक्वेशन परत सांगा तिला.
Chauthah. Which one? Okay. 4. This one, na? Okay.
येतो. हा.
Yes, na? आता have you got B?
Yes, sir. Yes, sir.
Now you just put this B in this equation. In this equation, you see this A plus B is uj minus ui divided by L. Okay. Sorry, not this equation. Sorry. Where you have to put? Okay, I will. Yes, you put in this equation. Yes, you put in this equation. You see this A plus B into uj minus ui divided by L xi. Okay. Over.
Sir.
Or now that you will get this one. How you will get here? Here in place of L, you use xj minus xi. Xj minus xi. Okay, I will solve it. Just a minute. I will solve it. Erase all. Here. Okay, I will take here. I will put in this equation. B is equal to now, or in which uj minus ui divided by L. Uj minus ui divided by L. Okay, I will show you here. Ui equal to A. What happens here? Ui equal to A plus B is uj minus ui and whole divided by L. Uj minus ui whole divided by L into xi. Okay, xi. Now you take this on this side. Okay, it becomes now. Can you solve this one yourself?
Hello.
Yes. If you are
Yes,
able
sir.
to, okay, I will show you in notes because it requires it is simple one, and it requires big typing also. Okay, I will show you. Here also it is solved like this. Okay, you solve this one by putting here. Okay.
Yes,
That
sir.
is uj
Got it,
minus.
sir. Sir.
Okay. Next one. Next is after calculation of the shape functions, you have to go for the third step, that is derivation of elemental stiffness matrix. And load vectors. Now see here, for deriving the elemental stiffness matrix and load vectors, we need some concept from engineering and mathematics. Now for structural problem, generally we are deriving the elemental stiffness matrix from principle of minimum potential energy, Now, what is the principle of minimum potential energy? See here, here I have written the statement. When structure is loaded and it attains the equilibrium position, the potential energy of the structure is minimum or must be minimum. Now see here, when I write the definition of the potential energy for the structural members, then you will get the clear idea. Okay, potential energy is the addition of strain energy plus work potential. Strain energy plus work potential means work done by the external forces. Okay, here I will write potential energy is strain energy plus work done by external load. Now strain energy is developed because of the internal resistance. Am I right? Strain energy is developed because of the internal resistance. Now you have studied the strain energy in second year. Can you remember or can you tell me what is the equation for the strain energy? Can anyone who has prepared strength of materials? What is the equation for the strain energy? It is half of the stress into strain into volume. Am I right? Half of the stress into strain into volume. Now stress is the internal resistance. That is resistance per unit area is stress. Do you agree with this? Therefore, the strain energy is the energy developed because of the internal resistance. Work done by the external loads. Now see here, when we consider the equilibrium condition, strain energy, that is internal resistance, equal to the external load. Okay, internal resistance equal to the external load, then your strain energy equal to the external work done by the external forces. Okay, but resistance and external load, these two things are opposite in nature. That means if we take the strain energy as a positive, then you have to take the work done by the external load as a negative. Here these two things are same and acting in opposite direction, therefore their effect is 0. Here in statement of principle of minimum potential energy, it is written as a minimum. Okay, you agree with this? Have you got this? Potential energy is minimum when structure is in equilibrium. Okay, now you have to remember this equation we are using for, or this statement or this concept we are using for deriving the elemental stiffness matrix and load vectors. Okay, or finite element equation for single element. When structure is loaded and it attains the equilibrium position, then potential energy of the structure must be minimum, and potential energy is strain energy plus work done by the external loads. Now what is the strain energy? We will write equation one by one because this requires the big derivation. Strain energy, this I have written in the notations, that is I is equal to pi plus W. Pi I am using notation for the strain energy and W for the work done by the external loads. Okay, now do you know this equation? हे equation माहित आहे का? This equation, do you know this equation? Anyone? Sresh, do you know this equation?
Yes, sir.
Yes.
Yes, sir.
Next. Can I go for next? Preeti, do you know this equation?
Yes, sir.
Okay. Strain energy density equal to the half of stress into strain is equal to half of stress. I have used the sigma as a notation for the stress and epsilon as a notation for the strain. Okay. Next, if you want to calculate the total strain energy, for calculation of the total strain energy, you have to integrate this equation over the volume. You have to integrate this equation. This is the strain energy per unit volume. Am I right? Now for calculation of the total strain energy, you have to integrate this equation. Now therefore strain energy, total strain energy is integration over the volume. So here these terms are wrong. Actually it is over the volume. Okay. Now, 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 this is integration of stress into strain over the volume. Now, in our problem, we have taken constant area. We have not taken variable area. We have taken the constant area. Therefore, integration over the volume, I can replace that over the area into dx. That is area into dx. That means dv I can replace by a into dx. A into dx, because my area is constant area. My area is constant area. Okay. Or can you get this one? I have replaced just the dv by dx. Now when we replace this dv by a dx, your integration becomes integration over the dx length. Okay, do you agree with this? Now for dx we have limits xi and xj. That means lower limit of your integration is xi and upper limit is xj, because your domain is starting from the xi and it ends at the xj. Okay, therefore limits of integration are xi to xj. Okay, next one, what I will do, I will write stress in terms of the strain. Now stress is product of modulus of elasticity and strain. This also you know. So your equation becomes half of modulus of elasticity into strain. This is your stress sigma into strain over ADX. Have you got it? Now when we take the product of these two, it becomes epsilon square, that is a strain square, that is half of E into strain square. Any doubt in this equation? If you have doubt, you can ask me. काय डाउट आहे काय? Rahul Shirke, are you listening me?
Yes, sir.
If you have doubt, you can ask me.
Yes, sir. No, sir.
No, na? Okay. Now after that, what I will do, I will replace this strain by the nodal displacement. How I can replace this stress by nodal displacement, I will tell you. You see this is the equation which I have written on last slide. Now half of E into epsilon square. I can take E and A out of the integration also, that I will do later. Now you see here I have taken AE by 2 out of the integration, that is xi of xj epsilon square dx. Okay, just this is a material property, it is a constant, A is a constant, so that I can take out of the integration. Okay, next one, now you have this element, if your node I is displacing with ui displacement and node j is going to displace with uj displacement, then we can write uj minus ui as a deformation. Of the element. Okay, do you agree with this? And strain is equal to change in length with respect to original length. That means uj minus ui is your deformation delta u. Okay, and we can write du by dx as a strain. Okay, you can write du by dx as a strain. You can see here du by dx, that is a change in length or change in position of the I node and j node. Okay, that is your deformation per unit length, and du we can write uj minus ui, and dx you can write xj minus xi. Okay, and this becomes uj minus ui divided by L. If you have doubt in the strain equation, you can ask me. Have you got it? Pratik Konmane. If you have doubt, you can ask me, I will explain it. Rakesh Patil.
No, sir.
Okay. You see here, this is the space period, suppose up to here. Okay. And this is the space period. Okay. Now, difference between these two is uj minus ui, and that is your deformation per unit length dx, and uj minus ui divided by xj minus xi, uj minus ui divided by L. Now this I can replace by uj minus ui divided by L. So your equation of strain energy, it becomes half of L square. Okay, it is uj minus ui square divided by L square. Do you agree with this? Uj minus ui square divided by L square. Now uj is constant, it is a nodal displacement. Ui is a constant, it is also nodal displacement. Length is also constant. So I can take this out of the integration. That is uj minus ui square divided by 2L square. Okay, L is constant, that I have taken out of the integration, and you will get only integration of dx. What is integration of dx? What is integration of dx?
X.
And when we put the limits, what you will get here? When we put the limits, it becomes xj minus xi. Am I right?
Minus XX.
And xj minus xi equal to L, length of the element. Okay. Therefore, you will get pi is equal to you see here. Here this integration is your L. This integration is your L, and this L will be cancelled with this L. Okay, do you agree with this? Now you will get AE by 2L uj minus ui. It's a square. Okay, and that is your strain energy. After that, I can expand this strain energy equation. You see here. Okay. I will go back to here. I will get here uj minus 2ui uj plus uj square, or I will write here ui square. Ui square minus 2ui uj plus uj square. Now, can you convert that into quadratic form of the matrix? That is ui square plus minus 2ui uj plus uj square. Already we have done this in second lecture, at the time of second lecture. Okay, do you agree with this? That is u transpose k u. We have done it. Now, by using that one, you refer matrix algebra or quadratic form of the matrix. That approach we have used here, and this quadratic term, or this is second degree polynomial, we are going to replace by this one, that is AE by L. It is u transpose, and this is k matrix, and it is equal to 1 minus 1 minus 1 1 ui uj. Same equation we have solved in matrix algebra. You go back and visit to that matrix algebra, that is quadratic form of the matrix algebra. You will get this equation. Am I right? Have you done it? Quadratic form of the matrix. Anyone? Prithviraj Kale. Okay. Shreyas?
हाँ सर.
केलं नाही?
हाँ केले की सर. Yes sir.
This same problem I have solved at the time of that lecture. Okay. Now you will get this u transpose. This is a k matrix, or this is k matrix and ui uj. Now what I will do, I will multiply by AE by L to this matrix. That means AE by L, half of AE by L into ui uj. Sorry, this is half just ui uj. Here it is AE by L minus AE by L minus AE by L AE by L UI UJ. Okay. Now this equation you will get. Now you can see here. Now your strain energy equation becomes U transpose K U. How it becomes, I will show you. You see here, half is as it is. For UI UJ, I have replaced that UI UJ by single notation, that is capital U. This capital U is a displacement matrix, that is a nodal displacement matrix. Nodal displacement matrix, and K is your stiffness matrix. That means when we multiply by AE by L to this matrix, you will get AE by L minus AE by L minus AE by L AE by L, that is your K matrix, and this U matrix is your nodal displacement matrix. You can see this one, K is AE by L 1 minus 1 minus 1 1. Next, U is your displacement matrix. Okay, you see this one here. I will take this equation number 10. Equation number 10. Here U is your UI UJ.
Sir,
Yes.
sir,
Yes.
the transpose get like a U matrix, huh?
This is a transpose, U transpose.
Okay.
And this is your U matrix. U matrix. That is transpose of displacement matrix, K matrix and U matrix. Okay. K matrix, and K matrix is AE by L 1 minus 1 minus 1 1. Okay. Now you will get this as a K matrix, and it is known as a stiffness matrix. AE by L 1 minus 1 minus 1 1. Okay. And this one is a displacement matrix. Okay. And your strain energy is half of U transpose K into U. Half of U transpose K into U. Okay. Now why it is called as a stiffness matrix? I will tell you why it is called as a stiffness matrix. Now, what is the definition of the stiffness? What is the definition of the stiffness? Can anyone tell? What is the definition of the stiffness? Yes. What is the definition of the stiffness? Akshay Patil, what is the definition of the stiffness? Stiffness म्हणजे काय असतं रे?
Ability to resist.
Stiffness.
The
What is
ability
unit
to
of the
resist
stiffness? What is
Newton per mm square.
Newton per, not mm square, Newton per millimeter, na?
Sorry.
Yes. Yes, Newton per millimeter. Am I right? Now it is the force required for unit displacement. Force required for unit displacement. Okay. Stiffness is force required for unit displacement. You have to remember. And here your displacement equation or deformation equation, force required for unit deformation. If I write the deformation equation, it is your PL by A into A. Am I right? You have studied this equation in the strength of material. That is force required for deformation equal to the force into length upon area into modulus of elasticity. This equation you have studied, that is delta L is equal to PL upon AE. Okay. Now I will write this equation for the force. Force is equal to AE into delta L divided by L. Am I right? Delta L divided by L. Okay. Divided by L. Now this, if I keep this as a unit, or if I take this on this side, that is P by delta L. P by delta L. I will write this equation P by delta L. What is it? It is a force per unit displacement. Am I right? Force per unit displacement. It becomes AE by L. Okay, AE by L. Do you agree with this? That means if you observe the stiffness matrix, each term is AE by L. Each term is AE by L. Okay. Therefore, it is a force required for unit displacement. Force required for unit displacement, or it is a force per unit displacement. So, this equation or this matrix is known as a stiffness matrix. Okay. And this is a property of the domain or property of the discipline, we can say. And this is a displacement matrix. Okay. Now this is a strain energy. I will stop here. Okay. Remaining part I will cover at the time of next lecture. Okay. If you have doubt, you can ask me. It is very important See here, I will stop the recording.